Welcome back to part 3 with Dr. Cofield and Chem 1. We're going to study properties of matter a little bit deeper. We're going to look at physical properties versus chemical properties, and then extensive and intensive properties, and then significant figures a little bit at the end of this section. So physical properties are what we use to identify substances by, okay? And you can use composition as well, which means what atoms are actually put together, but the properties a lot of times are easier to test for in the real world. And so properties could be quantitative, that is, we measure and we express a certain number, or it's qualitative, whereas it's pink or it's blue or it's, it smells funny or whatever. So that's qualitative. So a physical property is one that we can observe and measure without changing the identity of the substance itself. So you could also call this non-destructive testing, okay? So we don't change anything about the compound. Melting point is a physical change. So that's when you go from one state of matter to another. But the identity of that material or that matter doesn't change. So we have physically changed it from one state to another, but it's still that same material, okay? We can recover the original by cooling it down and letting it freeze again. So melting point of a substance is a physical property as well as freezing point. Chemical properties, on the other hand, are those that do change the properties and the composition of the material. After a chemical change, what you had when you started is not there anymore. And what remains is a totally different substance, okay? And you can't recover that by means of physical properties such as boiling or freezing. So we've destroyed it, we have turned it into new things, whatever, when we were doing chemical properties or chemical changes. Extensive and intensive properties are the opposite, okay? Measured values of an extensive property depend on the amount you have. Mass is an extensive property because if I have this amount, okay, that's a certain mass, but if I have this amount of the same material, it's going to be a higher mass. It's going to weigh more when I put it on a scale. The value of an intensive property does not depend on the amount of matter. So those are things that are kind of innate in that material, like density and temperature are intensive properties. They don't depend on how much you have. If you have a gram of material, if you have a ton of material, its density will always be the same. So this diagram shows a compound that's made of two elements, okay? And so you see that in this particular box, you've got a red and a green representing two different elements, okay? And so then they are in a liquid state because they're pretty close together, but there's some room in between them. And so the question is, which of these diagrams and the rest of them represent a physical change from the box A, and which represent a chemical change. And so when we look at these, and I've got a little more room in this next slide that I've done. Okay, so if I'm going to this one, all right, what's happened? I've had a rearrangement, okay? Instead of having one green and one red, now the reds are together and the greens are together. So I have rearranged that. And so that means that it is a chemical change because I have changed the identity going from one red and one green to two reds, two greens. Does that make sense? Okay. In this next one, it's also a chemical change, okay, because what I've done is I've taken where I had the red and the green hooked together, I have unhooked everything, and so everything is by itself, okay? So I have, again, rearranged. changed the identity, and so that's a chemical change. Now this last one might be a little confusing. I had to look at it myself. So you've got a red and a green and a red and a green. So we haven't changed the identity of that, but what we've done is we've gone from the liquid to the gas state. And so we just changed the state, therefore that is a physical change. Okay, so I hope, like, kind of seeing it in a picture form, that might make it a little more reasonable for you. Okay, and then you have your for practice problem, which you're going to go through and try to decide, is this a chemical change or is it a physical change? All right, so in section 1.5, we're gonna start this section. We're gonna just do half of it in this presentation. We're gonna look at significant figure rules, okay, and then we're going to do calculations and with measured numbers and accuracy in the next video. So chemistry makes use of two types of numbers: exact numbers, okay, and so those are defined values. So that's one of the a conversion factor, we call them. So these are equalities. When we use those, we're assuming that those are defined, so they have an infinite number of significant figures. If you count something, that has an infinite number of significant figures because it can't be point whatever. You can't have 2.2 kids. Now, when we do calculations, we might say the average is 2.2 kids, but you can't have 2.2 kids, right? So when you count something, you consider it to have also an infinite number of significant figures, and that means basically that you don't look at that when you're trying to figure out how many significant figures an answer can have. So conversion factors are treated as exact values. Remember that. And counting, the numbering of, counting something is also a direct number. So whenever we measure anything with any machine, it's going to be inexact. Now, the exact numbers we talked about, remember on the previous slide, are what you count and a conversion factor. Inexact numbers are what we measure, okay, because we're going to be eyeballing something with our little eyeballs, and we're going to be looking at a measuring device. And there's always an amount of uncertainty in the value of this number. And that uncertainty is in the form of a digit that depends on the units that you see on your measuring device, okay? So, and it's going to be that last estimated number that you come up with. And remember, you're using your eyeballs, your partner's using theirs, so you may differ on something. You may disagree on it, and that's totally fine. That's why that last number is inexact, and so it's an estimate by whoever is doing the measurement. So we use significant figures to tell us what is meaningful and what is uncertain. And so we can only be as certain as the least certain measurement. Kind of like that weakest link in a chain. So if you have a scale, what you're going to do, and it's a little bit hard to see with this color, but the meniscus goes kind of like this, okay? Whenever you measure in a glass device, you're going to have a meniscus, okay? It's because it kind of grabs a hold of the sides over here, but it droops down, and so you're going to always measure at the bottom of that meniscus, all right? And so you look at your scale. It's going from 3 to 4 to 5, okay? So how we look at this is we're trying to figure out what this level is. So we know it made it up to the 4, but it did not make it up to the 5. So our first number is going to be a 4. And then we look at this, and to me it looks like it's between 4.5. So this There's 10 of these marks in here, so each one is a 0.1 scale, right? So this would be 4.1, 2, 3, 4, 5. So it's between 4.5 and 4.6. So the next number is a 5. Now this last number is going to be an estimate, okay? So it's 4.5, and I think it's about halfway. So I'd call it 4.55. Now they're saying 4.56. That is that least precise number that you estimate at. And so I might think it's a 5, you might think it's a 6. So that's where that unknown or inexact part comes from, because it depends on who's using the measuring device and how accurate that measuring device is. So we're going to use the significant figures to tell us how exact the number is, okay? So any digit that's not 0 is going to be significant, okay? Any number is going to be significant. So this would have 4 significant figures. Zeros that are between non-zero digits are significant. So if you have a 0 between two numbers, that's going to be significant as well. So you would have 3 in the case of 305, and 50.08 has 4. Zeros to the left of the first non-zero digit is not significant. What's that mean? Okay, you got a number that's less than 1, and it's got a decimal, all right? These that are leading the number are not going to be significant, okay? So it only has 2 that are significant. This number, 0.00001, is got 1 significant figure, because all these others are just telling you how small that number is. Zeros to the right of the last non-zero digit are significant, okay? So if you have 1 and a decimal 0.200, those zeros are exact, they're exactly measured, and so that one has 4 significant figures. Zeros to the right of the last non-zero digit that doesn't have a decimal point are what we call ambiguous, okay? Ambiguous because if you write 100 here, I don't know if those are significant or not. So it could have 1, it could have 2, it could have 3 significant figures in the case of this. Now, I'll tell you, in our class, we typically consider, if it doesn't have a decimal place right there, that would be 1 significant figure. So that's kind of what I look at, but it is ambiguous, okay, because without additional information, you don't really know. Once I add that decimal place there, that tells me those are significant, and so it would then have 3 significant figures if it had a decimal place. So just 100 would have 1, but 100 point would have 3, okay? If I added another 0 there and I had 100.0, that would be 4. All right, so you'll practice with these and kind of, hopefully they'll make a little more sense. So to avoid ambiguity in such cases, we're going to express these in scientific notation. And in Appendix 1 of the textbook, you can find information about that. But if you have 1.3 times 10 to the second, that has 2 significant figures. This has nothing to do with it. 1.30 times 10 to the second would have 3 significant figures. So sometimes if you put it in scientific notation, a lot of times it will make sense. Like in the case of 0.0023 that we had a minute ago, if I put that in scientific notation, this is a little number, which means it's going to have a negative exponent. Anything that's less than 1 is going to have a negative exponent. So I would have to move this 1, 2, 3, because you can only have one number to the left of the decimal when you're doing scientific notation. So 2.3 times 10 to the minus 3. Now that shows me it's two significant figures. Why? Because you wouldn't put 002.3 times 10 to the minus 3. That doesn't make any sense, right? So that's one way of being able to tell with those leading zeros how many of these are significant. So let's practice a little bit with these and see what comes up. So all we're doing is saying how many significant figures. All right, so 443 has 3 significant figures because they're all numbers. 15.03 has 4 significant figures because even though it has a 0, it's between 2 numbers, so it's going to be significant. All right, so here's one of those I was talking about with that leading 0. Okay, there's 3 numbers and then a 0 telling us how little it is, so that one has 3. Because if I did that in scientific notation, that would be 3.56 times 10 to the minus 2, not 0.356. All right, 3.000 times 10 to the minus 7, since that has a decimal before those zeros, that is going to be significant. So you have 4 significant figures in that one. The 50, this is one of those that we say are ambiguous. And so the problem normally would have to tell you how many are significant, because you can't really tell from that. But like I said, a lot of times we'll just consider that it has 1 significant figure, but it could have 2. That's why we say it's ambiguous. All right, and then this last one, 0.9550, everything past that 0 that's not leading is going to be significant. So there's 4 in there. Okay, you may have to go back and look at this again if it's confusing you, because this is a little confusing. The only confusing part really are the zeros, and you got to remember, when to use, when the zeros are significant and when they're not. And then there you go. Here is your one where you can actually practice. And please, I hope that you will join me as I do calculations with these significant figures in part 4.